speaker, Jack Koolen, and his talk will be also about high symmetric graphs. So you are welcome.
Okay, thank you, Elena. So, can I start or?
Yeah, please, sure.
Okay, my talk is about bounding the intersection number C2 for a distance regular graph. So my talk will consist of three parts. First, I will talk about distance regular graphs. Then I will talk about our main result, and then I will talk about thin distance regular graph with classical parameters. So let's first start with the usual definitions of graphs. I think everybody in this audience know what they are. So for in this talk, all the graphs are undirected and simple. There are no loops nor multiple edges. The AGT matrix is a matrix where two indexed by the vertices such that x, y entry is 1 if they are adjacent, x is adjacent to y, and 0 otherwise. And the eigenvalues of gamma are the eigenvalues of its adjacent matrix. Note that they are all real numbers and that the adjacent matrix is diagonalizable. We will look at the distance between x and y, that is a shortest path distance. And if the graph is connected, we have d gamma, the diameter of gamma, that is the maximal distance between any two vertices. We will also need to set gamma I of x, and that are the vertices that are distance I from x. And we denote gamma x instead of gamma 1 of x, the neighbors of x. The subgraph induced on gamma x is the local graph of gamma at the vertex x and is denoted by delta x. So now we will introduce distance regular graphs. A connected graph is called distance regular and we abbreviate it to DRC, if there are numbers AI, BI, CI, such that for any two numbers, if I look at vertices x and y at distance I, there are CI vertices at distance I minus 1 from x, AI vertices at distance I from x, and AI neighbors of y at distance I from x, and BI neighbors of y at distance I plus 1 from x. So, for example, BD is always 0, and C1 is always 1, and B0 is the valency. So gamma is regular with valency B0, and that is just the cardinality of gamma 1 of x, the set of neighbors of a vertex. And clearly B0 is equal to Ci AI plus Bi, Ci plus AI plus Bi for all I. And for a distance regular graph, the following array is called the intersection array. Once you know BI and CIs, you also have the AIs, because AI is B0 minus CI minus BI. So now I should give some examples of distance regular graphs. I will start with the Hamming graphs. The vertex set is the vectors of length n with entries in an alphabet of order q, and two of those vectors are adjacent if they differ in exactly one position, and the diameter equals n. And if I take q is 2, then I get the normal n cube, and it is a distance regular graph with Ci equals to I. And this gives a framework to study codes, especially bounds on codes. For example, the Darsab-Linear program bound and the Schreiber bound gives bounds. And the Delsart linear programming bound use both Mesner algebra, and the Schrijver bound use the Terwillig algebra. So now we also introduce the other close related family of graphs. So now we take a set n of cardinality n, and now the Johnson graph J and T has as vertex set the set of T subsets of the set n. And two of those T sets are adjacent, T subsets are adjacent if the cardinality of the intersection of the cardinality of the intersection is equal to T minus 1. And clearly Johnson NT is isomorphic to Johnson N minus T, because you can go to complements. And this is really graph with Ci equal to I squared. And in a similar way as the Hamming graph gives a way to study codes, the Johnson graph gives an algebraic framework to study designs. So distance regular graphs were introduced by Biggs in the late 1960s as a combinatorial generalization of distance transitive graphs, which we will introduce now. On the other hand, Delsart introduced p-polynomial association schemes, and they are very closely related. And p-polynomial association scheme gives you distance regular graph, but distance regular graph can have more than one p-polynomial structure. So let now gamma be a graph. Now an automorphism is that maps edges to edges, and it's a connect graph is distance transitive if for any four vertices x, y, u, and v, such that the distance between x and y equals to the distance between u and v, there exists an automorphism phi of gamma such that x is sent to u and y is sent to v simultaneously. So a distance transitive graph is always distance regular and hence regular. But there are distance regular graphs that are not distance transitive. I will mention some examples later. Many of the distance regular graphs are distance transitive, but for example, a quadratic form graph of diameter at least 2 is distance transitive. So there are many, quite a few known infinite families of distance regular graphs. Many of them come from classical objects. So you have the Hamming graph, the Johnson graph, the Grassmann graph, the bilinear forms graphs, the Chesky linear forms graphs, and the dual polar graphs. They are all distance transitive. And one way to look at distance regular graphs is that you can study these classical objects from a unified combinatorial viewpoint. But there are also four known infinite families with unbounded diameter of vertex transitive graphs, but not distance transitive, namely the Ustimenko graphs, the Hamilton graphs, the Dub graphs, and the Egawa graphs, or the quadratic forms graphs. But there's one problem maker, the biggest problem maker, that is the twisted Grassmann graphs. These are not vertex transitive, and they have two orbits under their full automorphism group. So now I will go into the main results. I will first talk about motivation, why we should look at this. So in our paper with Van Dam and Tanaka, we had the problem 66, and that asks for the following question. If you have a co-connected distance graph, or you can also say for a distance graph of diameter at least 3, show that C2 is bounded by a function in B, where B is B1 over theta 1 plus 1, the ratio B1 over theta 1 plus 1, where theta 1 is the second largest eigenvalue of the distance Rayleigh graph. It's known that for a stronger Rayleigh graph this is true. That is that is shown by Neumann, for example. For distance Rayleigh graph, when the second largest eigenvalue is b1 minus 1, it is true because now we know all those distance Rayleigh graphs. And even for cuponorm distance Rayleigh graphs or for distance Rayleigh graph with classical parameters, it is not known. So in this, that is the paper, and I will come back. And in this talk, we will report on our progress on this problem. So I need some definitions. So a K-Rayleigh graph is when every vertex has the same number of neighbors. An H-Rayleigh graph with parameters vka, that is, every vertex has k neighbors, and if I look at an edge that lies in a common triangles, or they have a common neighbors, that is 1 and 2. A co-H-Rayleigh graph is the complement of H-Rayleigh graph, so a co-H-Rayleigh graph with parameters vkc is a regular graph with frequency k, and any two non-adjacent vertices have exactly c common neighbors. Note that if I take the complement of a co-H-Rayleigh graph, I get an H-Rayleigh graph, and the complement of a H-Rayleigh graph is a co-H-Rayleigh graph. We will need another term. So the mu graph, the mu xy graph of graph, is the subgraph induced on gamma x intersecting gamma y, on the set gamma x intersecting gamma y, where any vertex for the two vertices x and y at distance 2. And we call this graph mu graph regular with parameter k prime if each of the mu xy graphs for any two vertices at distance x and y at distance 2, any pair of vertices at distance 2, is a k prime regular graph. So now if you have an H-Rayleigh graph with parameter vka and a mu graph regular, suppose that your graph is H-Regular with parameter vka and mu graph regular with parameter k prime, then the local graph at any vertex set is co-H-Regular with parameters ka, k prime. This holds in particular for distance Rayleigh graphs, if it is mu graph regular, then because if you look at the neighborhood of C, then the common neighbors of X, Y, and Z is either in the mu graph of the neighbors of Z in the mu graph of the X, Y mu graph, or if I look at the locally at Z, then that in the local graph, the mu graph of X and Y has also the same amount of neighbors. So what it means is the local graph of the mu graph is the mu graph of the local graph. Yes. So what is our main theorem? So our main theorem says if you that C2 is bounded by a function B if you know that your A1 is large enough. That is, we need that A1 is large enough, otherwise then you can bound C2. So this gives some new progress in this particular problem. So I should talk about some tools. So everybody knows what is a complete bipartite graph. You take an R, KRT, you take an R set and a T set, and you take all the edges between them, yes? And our proposition is, if you have a disordered graph with frequency k and A1 is at most k over 2 minus 1, if gamma contains an induced k to t where t is at least 2, then any eigenvalue or theta of gamma, which is not the frequency, satisfies that theta is smaller e to k over square root of t minus 1. So that means that theta is fairly small compared to the k, yes? That the gap between the second largest eigenvalue and the k is quite large. So those graphs with that condition A1 at least k over 2, if A1 is at least k over 2 minus 1 and the diameter is at least 3, they were classified by myself and Jeong-Yuk Park. And there are only essentially the Johnson graph, the half cubes, and the distance regular line graphs. The distance regular line graphs, except for the polygons, they have diameter at most 4. So we essentially know all of them. Okay. So now I'm going to give a sketch of proof for that proposition. So now we will introduce the standard sequence for disordered graph and gamma with frequency k and intersection array AR B0, B1, B up to BD, C1, C2, and CD. And let theta be an eigenvalue of gamma with multiplicity m. Then the sequence satisfied the following recurrence relation with in the initial conditions. U0 is 1, U1 is theta over k, and the recurrence relation Ci times Ui minus 1 plus Ai times Ui plus Bi times Ui plus 1 must be equal to theta Ui for I at least 1. That is called the standard sequence. And the reason why we look at this, because there exists a map from the vertex set of gamma to the real m-dimensional Euclidean space, Rm. X goes to the head of X, such that the inner product X hat, Y hat is equal to UD, where D is the distance between X and Y. So now we prove the proposition. So now we have an induced subgraph KRT with color class X and Y with respective sizes R and T. Now we can look at X, capital X hat, and that is just a sum over X in X of X hat, and similar we can define the hat of Y, capital Y. Now we look at the gram matrix Q is with inner products X hat, X hat, X hat, Y hat, X hat, Y hat, and Y hat, Y hat. Then you can calculate that this is exactly this matrix. But this must be an positive semi-definite matrix, so therefore its determinant must be non-negative. And then you calculate the determinant, and then you take R2, and that finishes the proof. The polynomial you get is a little bit dirty, but in the end, you can show if with a little bit twisting, you can show the proposition. And now you can also reformulate this and that is we call our key lemma. So that says essentially the same thing. So that says that if you have a k2t, then t is at most 4b squared plus 1. That's just a reformulation of the proposition. It's not difficult at all. Then we need a result by Terwilliger, and I reformulated he showed quite a bit more than this, but I formulated what we need for this proof. So let gamma be an Disraeli graph with diameter at least 3, valency k, and second last eigenvalue theta 1. Let delta x be the local graph at vertex x. Then the smallest eigenvalue of delta x is at least -1 minus b1 theta 1 plus 1. So if I fix b1 over theta 1 plus 1, then this local eigengraph has a fixed bounded smallest eigenvalue. Now we are going to use the fact that if gamma is mu graph regular with parameter c, then for any vertex x, the local graph at vertex x is co-edge regular with parameters k, a1, c. So then, as the last ingredient, we need the following result by myself, my student Greben Michael, and my former student Jae-Yong Yang. Let theta be at least 2 be an integer. Then there exists a constant c theta such that for any co-Israeli graph with parameters nkc and smallest eigenvalue theta min, if theta min is at least minus theta and k is at least c theta, then one of the two of the following holds. Either c is very small or k is very close to n. And the second case really occurs, so we cannot, and this is really sharp out in the second case that follows from the Ramanujan graphs as constructed by Marcos Spearman and Srivastava. Okay, so now we have 3 ingredients. We have we have a bound on K2T. We have the result by Terwilliger, and we have this result by our 3. If you combine these 3 results, then you get the result of then you have the proof for the main result. So now I'm going to my last part of my talk, and that will be about thin distance Rayleigh graphs with classical parameters. So I will start with classical parameters. So that is with 4 or 3 parameters, d, b, alpha, beta. And the intersection numbers are expressed as in these formulas. I'm not going to pronounce them precisely, where this y j choose one is a Gaussian symbol, and that means it is bj minus 1 over b minus 1 if b is not equal to 1, and j choose 1 if b is equal to 1. If you look at C2, then you get exactly b plus 1 times alpha plus 1. So what I want to remark is all the known infinite families of discrete graphs with unbounded diameter have classical parameters or are very close related to infinite to some infinite family with classical parameters, like the folded hypercubes or the doubled Grassmann graphs. It is even conjectured by Barnay that this is really always the case. An important subproblem of Barnay's problem is to classify the distance Rayleigh graph with classical parameters with large diameter. And I want to remark that this isn't a very hard problem, as you have to worry about the twisted Grassmann graphs. I don't think that anybody really understands them yet. Another important subproblem is problem 58 of the survey paper by Van Dam, Ashimek, Tanaka, and myself. I already mentioned it before. Is to classify the thin distance Rayleigh graph with classical parameters. I will not define thin in this lecture, but we only need the main reason why the only reason we need thin is that we use a result by Terwilliger that shows that a thin distance Rayleigh graph with classical parameters of diameter at least 5 are always mu graph regular. But I will come back to this later. Note that it's also known that a distance Rayleigh graph gamma with classical parameters have that b is always an integer, but not equal to 0 or -1. If b is at least 1, then b is b1 over theta 1. Then b is equal to b1 over theta 1 plus 1, where theta 1 is the second largest eigenvalue of gamma. If b is at most -2, then they were more or less classified by Xu Weng. He classified, he got all the known families except for one unknown family with two parameter family. This family we have no examples of, but so most people will think that they will not exist, but we have no idea how to show that. Okay, so now I will go to my last section. I will talk about thin distance Rayleigh graphs with classical parameters. So as I already told you, I will talk about a result of Terwilliger. So, and it is in the Terwilliger lecture notes which were edited by Suzuki. So it is in the last lecture, lecture 40. So let gamma be a thin distance Rayleigh graph with classical parameters d, b, alpha, beta, where d is at least 5. Then gamma is mu graph regular. So as an application of our main result, we obtain the following result. Let gamma be a thin distance Rayleigh graph with classical parameters. Yes, with Felix k, diameter d at least 5 and b at least 1. Then there exists a constant CB, so that if A1 is larger than CB, then C2 is at most this number. So we need here that A1 is large enough to get this bound. But what has this to do with Barnay's problem? Then it's as follows. If we have a thin disarray classical parameters, where with Felix k diameter d at least 3 and b at least 1, if C2 is at least b plus 1 and d goes to infinity, then A1 also goes to infinity. So as a consequence, and the reason why this proposition holds is that in this case, alpha is at least 1 over B1 plus 1 because C2 is 1 plus alpha times B plus 1. So that as a consequence, we get the following. If the diameter is very large compared to B, we don't care what alpha beta are. It only depends on D and B. It has nothing to do with alpha and beta. Then the C2 is bounded by this function in B. It's about 4 times B to the power 5. And hence, we get that if D is very large, then alpha is bounded by this function in B. That's about 4B squared, 4 times B to the power 4. Why is this true? Because C2 is 1 plus alpha times 1 plus B. So now we come to almost the end of this talk. So now we discuss a result of Klaus-Metz of 1999. So if you look at if you don't have a Grassmann bilinear force Hamming graph or Johnson graph, then beta is bound in terms of D, B, and alpha. So you get 3 plus epsilon parameters if you're not in one of those 4 families. That is what his main result, or what his result says. And now we can also use our result and combine this result together. This says if D is much larger than B, then both alpha and beta are bounded in terms of D and B. Okay, but I only discuss distance radical with classical parameters. You can do the same thing for Q polynomial, but you have to be careful. The eigenvalue, which everything works the same as long as the eigenvalue that is the eigenvalue as first in the Q polynomial ordering is a positive number. That is what it is. So you can do the same thing for Q polynomial disrelica, but classical parameters make life slightly easier to discuss them. Okay, this is the end of my talk. Thank you for your attention.
Okay, thank you very much for your talk, Jack. Are there any questions?
Yeah, can I ask a question?
Yeah, sure, please.
So a few slides back, you had a result about A1 going to infinity. About,
yes.
Can you? I didn't get exactly the statement. So can you show the slide?
This one, this proposition.
I don't.
Oh, so
yeah.
what?
Yeah, this one.
I mean, so you can look at the parameters for A1, and that is some function D, but you have to multiply with an alpha somewhere, and if this alpha is large enough, and here we have that alpha is at least 1 over B1, B plus 1, so it's a positive number bigger than bounded away from 0, yes? So if you look, it's just a consequence of the classical parameters. You look at the expressions for A1 and then it's NK, then you see immediately that the exact statement.
So this is a global statement about distance regular graphs with classical parameters. I
Yeah,
mean,
it
so
does not- Yes.
yes, okay. Yeah.
Okay, thank you. Mhm.
Can I ask another question?
Yeah, sure, please.
You're referring to Banai's theorem, and that your bounds
Problem,
for
I
C,
think.
your sorry,
I think Banai's problem, no?
Banai's problem. Sorry, yeah, and your bounds for C2 help there. But if you consider the Banai-Ito conjecture, which is proved,
At least it is the first step into.
so if you consider the Banai-Ito conjecture, so there are finitely many distance regular graphs for given k, does it help to classify these further? So if you take small k,
I'm not so sure. I mean, I think that is not so trivial. No, it's not so
so
easy.
that the bounds are still too weak for that.
I think so.
Even though, of course, they're much stronger than in the proof.
Yes,
Thanks.
they are. Yes.
Thanks.
And then any other questions? Any comments? Okay, let us thank Jack again. Thank you very much. And it was really very nice talk with some explanation, I mean background explanation, and with new results. Thank you very much.